Metal oxide sensors target microplastic pollution. Microplastic detection has long relied on laboratory-heavy techniques such as Fourier transform infrared (FTR) spectroscopy. While precise, these methods are resource-intensive, time-consuming, and difficult to scale for continuous monitoring. As scrutiny of microplastic contamination increases across water systems, food supply chains, and industrial discharge, that limitation is becoming more pronounced. Researchers at Jeonbuk National University are examining an alternative: electrochemical sensing platforms based on metal oxide electrodes. Rather than identifying plastics through optical signatures, these systems detect changes in electrical behavior when microplastic particles interact with engineered electrode surfaces. The shift moves detection away from complex lab workflows toward potentially faster, simpler measurement systems. Moving beyond laboratory constraints, traditional spectroscopy has played a central role in confirming microplastic contamination, but it was not designed for routine distributed monitoring. Sample preparation, specialized equipment, and trained personnel remain barriers to high-frequency testing in operational environments. Electrochemical sensing approaches detection differently. When microplastics come into contact with a functionalized metal oxide electrode, they alter impedance and generate measurable current transients. These electrical responses can be tracked in near real time, reducing dependence on centralized laboratory infrastructure. For utilities, environmental agencies, and industrial operators, this model supports more frequent testing closer to the point of risk, whether at a wastewater discharge outlet, within a drinking water treatment facility, or at a marine monitoring station. The emphasis shifts from retrospective confirmation to ongoing measurement. Engineering sensitivity through materials design. Performance improvements are closely tied to material selection and surface engineering. Metal oxides such as zinc oxide, titanium dioxide, and cerium dioxide offer high surface areas and favorable electrical properties, increasing responsiveness to trace concentrations of plastic particles. Morphology plays a critical role. Nanostructures, including nanowires, porous films, and nanorods, create localized interaction zones that enhance signal strength compared to smoother electrode geometries. Surface chemistry further refines detection capability. For example, hydrophobic coatings can be tuned to attract commonly used polymers such as polyethylene and polypropylene, improving selectivity in complex matrices like seawater or industrial effluent. These design variables allow developers to adapt sensor configurations to specific use cases. Drinking water applications may prioritize sensitivity at low concentrations, while industrial monitoring may require durability in chemically variable environments. The result is a more modular approach than traditional one-size-fits-all laboratory instrumentation. Operational and data implications. Portable electrochemical systems could enable on-site screening without the delays associated with off-site laboratory analysis. Handheld devices may support inspectors conducting spot checks, while fixed installations could provide continuous monitoring in rivers, reservoirs, or discharge points. The relatively low power requirements and simplified hardware open the possibility of distributed sensor networks. Over time, this could generate higher resolution datasets than periodic sampling alone, offering improved visibility into contamination trends. Future integration with connected platforms may extend the value further. Sensor outputs could feed into digital monitoring systems for compliance tracking, risk assessment, and performance benchmarking. For organizations facing increased regulatory and stakeholder scrutiny, scalable microplastic detection may move from an experimental capability to an operational standard. While laboratory spectroscopy will remain essential for validation and detailed characterization, electrochemical sensing platforms suggest a complementary pathway, one focused on speed, accessibility, and deployment at scale.